I'll begin with a word of prayer. Dear Father, we thank you for this day. Thank you for the break and time to relax and refresh. Just pray you to be with us this week, that we would be able to renew our efforts and just to glorify you in what we do, Lord. In your name I pray. Amen. Okay, so you guys had a good break. Kind of a short break, but I don't know. Nevertheless, hopefully good. So I have just a little bit left in the section, I guess it's 2.9, which is on factor groups. By the way, something I forgot to say last time, but I should say, is that a factor group is often called quotient group. I may have said that. I don't remember if I did, but these are not different ideas. Factor group is the quotient group, different term for the same thing. Anyway, so the question I want to begin with, this is sort of the end of the section, which was, when do cosets HA and HB commute in the factor group, or the quotient group, if you like, of G by H? Of course, here, in order for that to make sense, what am I assuming about H? It's what? Well, a subgroup, yes, but more than that. Normal subgroup, right? If H is not normal, then we can't very well form the quotient. So what does it mean for HA and HB to commute? We have HA, HB, so that's what? By definition, this is HAB, right? Let's see here. Now, if that's, on the other hand, if we look at HB, HA, we get what? HBA, right? So if we have 1 and 2, if these are equal, so let's see here, HA equal to 8, good grief. HAHB equal to HBHA, in other words, that these cosets commute, right, is the same as saying that HAB is equal to HBA, right? And what does that mean? This quality of these cosets we measure by having that AB times BA inverse, right, is an element of what? H, right. In other words, using sock shoes, we've got AB, A inverse, B inverse is an element of H, right? That's the condition which is needed for these cosets to commute, right? Now, this quantity right here is so important that it gets a name. This right here is sometimes called the group commutator. Or if you're a group theorist, you'll just call it a commutator. But for me, commutator means possibly something different. But this is group commutator. And someone's also denoted A comma B like this. AB, A inverse, B inverse, all right? That's the group commutator. And it has a couple of special properties. Properties of the group commutator that are not too hard to derive. What would the inverse of the commutator in a group be? Let's calculate it. It'll take us just a second here. AB, A inverse, B inverse. Inverse is what? B inverse, inverse, A inverse, inverse, B inverse, A inverse, also known as B, well, let's see here how to say that. I don't know if that's helpful or not. See here, that's B, BA, B inverse, A inverse. What's that? Oh, that's, did I do that right, that last one? I'm not sure about that. Which is what? Is it the comment? That's what I'm wondering. Oh, it is. I'm sorry, I'm not used to it yet. Thank you, you guys. Good. So, yep. No, that's what's in my notes. What do you know? Math is math. Okay, good. So you don't have to memorize it. You can actually derive it, right? And also, if we calculate G, commutator AB, G inverse, guess what it's equal to? What if we conjugate the commutator? What happens? So I'll write it down. That's G, A, B, forgot my definition already, A inverse, B inverse, G inverse. And you just stick in copies of, so that's G, A, G inverse, G, B, G inverse, you know, G, A inverse, G inverse, inverse, oops, I'm sorry, G, A, G inverse, and then G, B, G inverse, inverse, which is G, A, G inverse, G, B, G inverse. My second step is not entirely obvious, perhaps, but what happens if you work that out? You get G, A inverse, G inverse, right? And so the G inverse is the identity, which was here. I'm inserting a G inverse G here. It's just kind of sneaky the way I did it. And likewise over here, there's a G inverse G that I stuck in there, or vice versa. Anyway, this is an identity. So anyway, get to the point here. Definition. If we let G prime is equal to all, it's the set of all finite products of commutators from G. All right. In other words, G is generated, here's this presentation, it's A comma B, such that A and B are in G, something like that. Although I'm slightly worried. I don't remember if this actually has, I mean finite products, though. I'm not sure if, I think that only counts for finite products, right? So, yeah. Anyway, this is the so-called derived subgroup of G. All right, G prime is the derived subgroup of G. Yeah, funny notation, huh? Derived subgroup. And good news, theorem, G prime is in fact a subgroup. That's good. If we're going to call it a subgroup, I should hope it's that. And you know, the fact that it's closed under inversion is already clear from the green calculation, right? Now, this doesn't directly give you that it's closed, but this formula is useful for showing that the derived subgroup is closed. I won't go through the actual details, but you can use the blue calculation to prove closure of the derived subgroup, yeah.
In the definition, you have G prime is equal to all finite products, and then G is equal to...
Oh, yeah, there is a very important thing missing. There. Yes. Thank you very much for that. Theorem 3 of section 2.9, which pretty much tells you why we're even talking about this. It's the following. The derived subgroup is a normal subgroup of G, and the quotient group formed by factoring the derived subgroup is abelian. So the factor group by G prime is abelian. And 2, if we have G prime is a subset of H, that's true if and only if H is a normal subgroup of G and G by H is abelian. See here, the proofs are in section 2.9. I'm not going to go over the proofs of these here. I just want to try to appreciate, like, what is this saying? So how are we forming this derived subgroup? We're taking all possible commutators, right? And what is the commutator? What is the idea of the commutator? It is basically quantifying what it means for these cosets to commute, right? So what does that mean? You mod by that. You're essentially forcing the cosets to commute by doing that, right? So that's why it's abelian. And number 2 says that if your subgroup contains the derived subgroup, right, then it has to be normal in G, and the factor group you form by H is abelian.
Are we assuming that H is a subgroup?
I think so. I think this is for H a subgroup of G. I think that's right.
In the book, it's got that.
Yeah. Yeah, that needs to be there. Thank you. So what can we say about, like, intuitively, what is G mod the derived subgroup? What's G mod G prime? What is this in terms of factor groups of G? What is it? I mean, G prime is in some sense the smallest, right? It's the smallest group in G where the quotient of G by G prime is abelian, right?
Kind of like the maximal abelian subgroup.
It's the minimal,
Okay.
which it's the minimal abelian. It's the minimal abelian. It's the minimal normal subgroup for which the factor group is abelian. But the smaller the thing you divide by, the bigger the quotient. This gets back to what I'm going to have trouble with in the next hour. You know, we're in series and sequences, and we're looking for inequalities. We have to do things like to make the numerator bigger, to make the denominator smaller in terms of, you know, how the inequalities go. It's the same issue here, isn't it? But but the smaller that is, the smaller G prime is, the bigger G mod G prime is, right? So, yeah, G mod G prime is the maximal. It's the biggest factor group you can get, which is abelian. So in a stupid, here's like the, so stupid case, if, what happens if G is abelian? What's G prime? It's just G again, right? Oh, excuse me. No. If it's so the factor, the derived subgroup and the center are kind of dual. So if G is abelian, we've got a couple things. On the one hand, we have that the center of G is G again, right? But if we have that the derived subgroup is just the identity, or you might say 0. So in fact, if G is abelian, then G mod G prime is just G again, right? Abelian group is the biggest normal subgroup of itself, which is abelian. Well, it's the biggest factor group formed from itself. But anyway, so these, in some sense, these are dual, and there's a little bit more in the text on that than just that. But all right, well, I just wanted to make sure we have talked about this idea. We may do more with it as we go on. I'm not sure.
When you say that the center and the derived subgroup are dual, does that mean that z of g prime is equal to?
I'm using that not technically, but metaphorically. When I say that they're dual, I don't mean anything much by that. I think there's an example in the book where they're equal.
Oh.
Yeah. Okay, so that brings us to one of the central theorems of the course. Section 2.10 discusses isomorphism theorems. And so what I'm about to prove for you is the so-called first isomorphism theorem, although that's not what your textbook calls it. For shame. So by my count, this is lecture 17. I could be wrong. I would say the first isomorphism theorem. You're like, there are more? Oh yes, there are more. We'll get to those soon enough. So the first isomorphism theorem. And so just to remind you, in case you forgot, we have definition for alpha going from G to H, a group homomorphism. What did we define So he's finally getting back to prove some things I've already proved for you guys. Right? In particular, I've already proved for you that the image of alpha, which is also known as alpha of G, right? In fact, we've already proved that that was a subgroup of H. And we also already proved that the kernel of alpha, right, which is alpha inverse of 1, we've proved that that's a subgroup of G. Now, I'll remind you more specifically what that means. That's alpha of x, such that x is in G. That's the image. This is, let's say, k in G, such that alpha of k is equal to 1, right? The inverse image of the identity, the forward image of the domain, or just the image. But we've already proved another day, in fact, that this is a subgroup of H, and this is a subgroup of G. Furthermore, we already proved another day that alpha is 1 to 1 if and only if the kernel's what? Just in continuity identity. Right? And if you've had my linear algebra, you well remember that I emphasize this in linear as well. Linear transformations are invertible. That means they're 1 to 1 if and only if the kernel is just the 0 vector, right? We do that. But, so those things are in this section, but I won't prove those again because we already proved them. But there's a little bit more. So here's the little bit more. This is the new part of Theorem 1. Theorem 1, just the new part. Okay, I'll just do the new part. The new part is that the kernel of alpha is a normal subgroup of G. Right? So I already have that it's a subgroup from our previous lectures. Right? So I'm going to focus on the normality part. So let's let x be an element of G kernel alpha G inverse, right, for some G in G. So here's the proof. I'm assuming, of course, as I will throughout the rest of this lecture, that alpha is a group homomorphism, all right? So what would I like to show? I would like to show that x is actually an element of the kernel. Because showing that will show that this conjugate of a kernel element is again in the kernel again, which would show that the kernel is a normal subgroup by our normality test, part 2. So what do we got? What's the test? How do you check if x is in the kernel or not? Calculate alpha of x, right? What's alpha of x equal to? Oh, I'm sorry, I've forgotten something. This is kind of important. Observe, there exists k, right, in kernel alpha, such that what? Such that x equals to gk, g inverse, right? By definition, I mean, if I say x is in this set, that means that, and sorry guys, there's something I must apologize for. So sorry. I can't decide. Is it capital? Is it lowercase? I don't know.
I think it's lowercase.
Yeah, but for me, I don't know. Yeah, it is lowercase in the book, but as you can see, already, look here. I used lowercase here. I used uppercase here. So it's indeterminate for me. Sorry about that. Anyway. Okay, so anyway, alpha of x then is alpha of gkg inverse. But this is a homomorphism, so that's really alpha of g, alpha of k, alpha of g inverse, right? But what's alpha of k equal to? Remember, k is in the kernel. Alpha of k is 1. And so we got alpha of g inverse, which is, of course, alpha of g inverse, which is alpha of 1, which is 1. You could have also pulled the inverse out of the homomorphism by the inverse homomorphism property and just canceled them up there. It's up to you, whatever. One way or another, we get that alpha of x is 1, which shows what? X is an element of the kernel of alpha. Yes, sir? Yeah, alpha is a homomorphism. Day 1, we proved that homomorphism takes 1 to 1. maps the identity to the identity. Yeah. Good question, though. So, I mean, I'm not giving you a very, here's the more complete answer. It was alpha of 1 times 1 is alpha of 1 times alpha of 1, but it's equal to alpha of 1. Then by cancellation, we get alpha of 1 is 1. But, yeah. That's a less jerky answer. Let's see here. So this then shows, of course, that G kernel alpha G inverse is a subset of kernel alpha, which tells me then that kernel alpha is a normal subgroup of G, as little g was arbitrary, right? That shows that the kernel is a normal subgroup. Now, so there's two, as he mentions in the book, there's two important subgroups for homomorphism. The one is the image, the other is the kernel. We have no expectation that the image is going to be normal. The image doesn't have to be normal. He gives the example, if you just take a non-normal subgroup of a group and just look at the inclusion map, the image of a subgroup under the inclusion map is the subgroup again, and of course it doesn't have to be normal, so we don't really expect much about the image before the fact, all right? It's a subgroup, yes. Is it a normal subgroup? Maybe, maybe not. But kernels are special. Theorem 2, and anyway, I'll just state it. Theorem 2 is if we have K is a normal subgroup of G, then K is equal to the kernel of phi, where phi mapping from G to G mod K is the coset map. All right, so we've already talked about this coset mapping before. What have we already proved about the coset mapping? So let's see here, phi of G is what? It's equal to Kg, right? So this is a well-defined homomorphism from G to G mod K. This we have worked out another day, I believe. All right. Although I don't think there's really much. The well-defined is not hard here. I'm not the domain's not a coset, it's the range. So there's really no ambiguity when I write phi of G is Kg. Okay, that is single valued. Homomorphism property, I mean, we can go through that again. Here, watch. Phi of AB is KAB, which is KA, KB, right? That's well defined because K is normal, right? And so that's phi of A, phi of B. So there you go. It's a homomorphism. So what's left to prove in this theorem? Really just that K is the kernel of phi. So let's look at that. So let's let X be an element. X be an element of the kernel of phi. What's that going to make? What's that look like? So that means that phi of X, right, is equal to 1 in the where? The 1 for G mod K. What is that, though?
Just K.
Yeah, it's just K. So in other words, we have that Kx is equal to K, right? What's that mean? Right. Okay. So there, that indeed. So thank you. Sorry, not the greatest format. But anyway, yes. So the point is, thus, K is in fact the kernel of phi. Yeah. So there, so here's some examples. One, we could say alpha of z equals the modulus of z, where alpha is mapping from the non-zero complex numbers to the real numbers, positive real numbers. Maybe that's supposed to be, I think it's supposed to be a star. Yeah. I got a plus in my notes, but I think that's wrong. 2, it's not real numbers, but anyway. Oh, I'm sorry, I forgot my notation. So our plus is, thank you, it's this thing, right, under multiplication. That is, in fact, a group, right, a multiplicative group, just the positive reals.
Does it matter which one we use?
There are three sort of natural groups to think about with the reals, maybe at least 3. There's the group, the whole reals under addition, right? That's an additive group. There's the non-zero reals under multiplication, right? Positive and negative, but not 0, right? And then a subgroup of that is just the positive reals. So there's these like 3 sort of natural groups attached to the real numbers. In this case, just the positive reals. Yeah. So what's the kernel of alpha here? It's z such that the modulus of z is equal to 1, right? In other words, it's the circle group, which we denote c up for 0. 2, you could look at alpha of a equal to the determinant of a, right? So here alpha would be a mapping from where? From G ln R to, again, non-zero, well, this not again, but this time non-zero reals, R star. In fact, that's a homomorphism, right? Because the determinant of AB is the determinant of A, determinant of B. What's its kernel? Right, it's A such that the determinant of A is equal to 1, which of course we call SLN R. So there you go. We proved this a different way the other day, right? We proved directly that SLN was a normal subgroup of GLN. But I'm telling you now, a different way and a simpler way to argue that is just to say, oh, okay, this determinant mapping is a homomorphism. Its kernel is SLN, therefore SLN is a normal subgroup of GLN. Right? We don't have to check the normality. It suffices to prove that alpha is a homomorphism from GLN to SLN. Right? Because if you look at this calculation we did over here, this is exactly the calculation we did in the context of GLN SLN example to prove normality of SLN. So rather than keep doing that for every example, we just say, hey, you know what? It's true for homomorphism that you can pull the G and G inverse out like this for the kernel. So just once and for all, we have this theorem, we can apply it. 3. I guess it's a question of division of labor, right? G a group, and if we have G is in G with the order of G being n, all right, then we can define alpha from the integers to G, all right, by alpha of k equals, how's it go? Oh yeah, G to the k. I'm sorry, I'm an idiot. Oh no, what? Sorry, I just saw some of the dust moving, it was disturbing, but that's just my peripheral vision messing with me. So alpha of k is G to the k, that's how we assign the integer k. So what does it mean, what's the kernel of this mapping? Because if we can find it, we know it's a normal subgroup of the integers, right? So if we set this equal to 1, which is to say that k is in the kernel of alpha, right? What does this mean? G to the k equal to 1, but G has order n. What does that imply? N must divide what? Must divide k by our earlier work, like section 2.4, I think it was. And so that implies that k is equal to nj. In other words, it's an element of nz. So put this all together, we get that the kernel of alpha is nz. Example 4, you may remember from the test, the sign is a homomorphism from the symmetric group on n elements to the group 1 minus 1, right? And here, of course, we have sign of sigma equals to 1 if sigma is an an, and minus 1 if sigma is not an element of an. Since every permutation is either even or odd, that suffices to define sigma, and it's simple to check that sigma is a homomorphism. All right. What's the kernel of sigma? Right. It's sigma in is an Sn such that sign of sigma equals to 1, also known as an. So yet another argument that the alternating group an is a normal subgroup of Sn. We argued last class, I believe, that it's a normal subgroup because it has index 2. It's another way to argue that it's a normal subgroup. It has index 2.
Internal sign, right?
Oh, yes. Thank you. Much appreciated. Yeah, I wouldn't know. Yeah. Yes. Thank you. Thank you. What time is it? Sorry.
42.
What's that?
242.
2:42? All right, we're good. I hate to rush this theorem, so I don't want to rush it. Where are we? We're good. We can do it here. So finally, we reach theorem 4. Theorem 3 we covered in a previous class, guys. So this is theorem 4 of section 2.10, which I would call the first isomorphism theorem. All right. And the theorem says this: if we have alpha that goes from G to H, a group homomorphism, all right, then the image of G under alpha, alpha of G, is isomorphic to G mod the kernel of alpha. There you go. So I'll prove this in a couple stages. Number one, we're going to let follow the Nicholson, and I'll say K is kernel alpha. All right. And I want to study what does it mean for cosets of K to be equal. All right. So what does it mean for KG1 to equal to KG2? What's an equivalent condition to that? Right, so of course I'm saying suppose, sorry, I forgot my G1, G2, where are they? So one of my pet peeves with you guys in like incomplete theorems is biggest criticism probably across the board of proofs at this level for you guys is you don't tell me where things are, right? So, I mean, it's kind of stupid, but these are in G, all right? So anyway, KG1 equal to KG2. This is equivalent to what? You just told me, was it G1, G2 inverse being an element of what? K. Right, which is equivalent to saying that alpha of G1, G2 inverse is equal to 1, right? Which is equivalent to saying that alpha of G1, alpha of G2 inverse is equal to 1 by properties of group homomorphisms, right? Can pull the inverse out. And that's equivalent to saying what? Right, alpha of G1 equals to alpha of G2. So let me call this calculation we just did here, this list of equivalents that we have determined, let me refer to this as star. Okay? So by star, I can define a mapping we'll call alpha bar following. I hate to erase this because, I mean, if you don't mind, let's just, before I erase this, this is kind of bad, but in the interest of making the most of my writing over here, we can apply the isomorphism theorem to those examples, right? But we have to be careful. We should apply it to the image. Like, what's the, is this, in other words, like number one, is alpha a surjection? Is it onto? Yeah, any complex number you can, I mean, any real number, you can find a complex number that has that as this modulus, right? Like, that real number will work. Positive real number. So it's definitely onto. So what's this? I mean, if you apply the first isomorphism theorem to this, we get what? Applying the first isomorphism theorem to my first example give me what? We get C non-zero mod C0 equal to, well, isomorphic to R plus, right? I think we had a homework problem that kind of scratched at that, right? You looked at the cosets, concentric circles, indexed by the radius. That's what this is again. This one would say what? This one would say that GLN R mod SLN is what? Again, I think it's surjective. You definitely can find, give me any matrix, I can find you, I mean, give me any positive real number, excuse me, any non-zero real number, I can find you a determinant. I can find you a matrix which has that as its determinant, right? Do you know? How about this? Oh, thank you. Yes, exactly this guy. So that shows you that for any non-zero C, this is in GLN. So that shows you it's onto. Consequently, you know, alpha of GLN R is equal to non-zero reals. So anyway, here we go. So that factor group is isomorphic to the non-zero reals. This theorem is really nice, right? And these would not be as much fun to prove directly, right? You'd have to find the isomorphism. You could do it. This one, well, enough. That's a flavor. Let me go on with the proof.
Is alpha of G equivalent to H?
I'm sorry?
Is alpha of G equivalent to H?
Alpha of G equivalent to H. No. This is only, okay, so you can add a sentence to this. If alpha onto, then H is isomorphic to G mod the kernel of alpha. But we do not assume that alpha is a surjection in this theorem, which is why the isomorphism is not to H, but to the image. Okay, so moving on here, we can, now I've cluttered my, look what you did to me. Does everyone have this? Because I'd like to erase it now. Curses. Sorry about that. So let's define alpha bar, all right, of kg equal to alpha of g. for all kg in G mod k, right? This makes sense as k equals to the kernel of alpha is a normal subgroup of G, so I can form the quotient, right? If I didn't know the kernel was normal, we'd have to prove that here, but we already proved it in the last theorem, right? And star shows that alpha bar is well defined, right? In other words, that alpha bar of kg1 is equal to alpha bar of kg2 whenever kg1 equals to kg2, right? Star proves that that's the case. So this alpha bar is well defined. It's a mapping from where? So alpha bar is a mapping from where? It's a mapping from the cosets of G by K to where? To alpha of G, right? It's easy to show that alpha bar is onto. Alpha of x in alpha of G has alpha bar of kx equals to alpha x. So therefore, alpha bar is a surjection. Is it a homomorphism? What if we take alpha bar of kx times ky? What's that? That's alpha bar of what? Kxy, right? By definition of multiplication in G by K in the vector group. And then that is by definition alpha of xy, right? Which is then alpha of x times alpha of y. So here's definition of alpha bar. This was multiplication in G by K. This is because alpha is a homomorphism. And then what is that? This is alpha bar of kx. This is alpha bar of ky. So there you have it. Alpha bar is a homomorphism. Now what am I trying to show? I'm trying to show that the image of G under alpha is isomorphic to G mod the kernel of alpha, right? So if I could show that this alpha bar was a bijective homomorphism, we'd be good to go, right? That would be it. I've got that it's a homomorphism. I've got that it's onto. What am I missing? One more piece in the puzzle and we're done, right? We need to show what? 1-to-1, right? Remains. So consider, let's see here. I mean, I guess we could do it directly. I'll just do it directly. Alpha bar of kx equal to alpha bar of ky. What's that mean? Alpha of x equals to alpha of y, right? But what's that mean? Alpha of x, alpha of y inverse is equal to 1, right? Which implies what? That implies that alpha of x, y inverse.
We could just use star directly.
Use star directly. Oh, thank you. Yeah, I'm sorry. I'm reinventing the wheel again here. As you notice, I'm starting to trace back through these steps, right? No accident there. So Sam is right. I should be lazier. This implies I should just, where should I go? Let's see, where should I,
Alpha x equals alpha y, and then you get k x equals q1.
yes. Okay. Sorry, let me be lazier. Thank you. Very good. Hence, alpha bar going from where? From G mod the kernel of alpha to the image of alpha is an isomorphism. All right. Well, there's some nice examples, but I probably should, as much as I really, really want to look at those examples, I probably should take the last 4 minutes to talk about the corollary. We'll get to the examples next time, I suppose. The examples are legion. I mean, this theorem is so stupidly useful, it's hard to overstate. But here's the corollary. If alpha G goes to H, group homomorphism, then alpha factors uniquely as alpha equals to alpha bar phi, where phi is the coset map, and alpha bar is the mapping from G mod the kernel of alpha to H. And this isn't he says it's defined in the proof of the first isomorphism theorem. This is an abuse, because he has not assumed that, like, alpha bar is a mapping to alpha of G. And I object to him saying this is the same thing as in the proof. In the proof, the codomain is not H. The codomain is alpha of G. He is switching the codomain to H in this corollary. And he's saying it's the same thing. And that offends me, because you guys, I want you to be careful about the distinction between this being H and this being alpha of G. Those don't have to be the same thing. And those are technically different maps. So, like, maybe I should call this alpha bar bar or something, just to be pedantic. But anyway, here's the thing is, this picture really is worth all of my words. So here, alpha, H, it's nearly as in, I mean, it's almost the same thing as in the proof of the theorem we just did. It's just the codomain is being traded for H instead of alpha of G. That's all I'm saying, guys. So here's the interesting part of the proof. If we take, I'll do it over here. If we do alpha bar of phi of x, what do we get? This would be, by definition, alpha bar of phi of x. What's phi of x? Phi of x is the coset map, right? So that's alpha bar of kx. So the rule for alpha bar is the same as we were just talking about. Admittedly, the codomain's different. In other words, alpha bar doesn't have to be a surjection. Anyway, this is still alpha of x, right? But x being arbitrary, this little calculation I did shows you that as maps, alpha bar composed with phi is equal to alpha again, right? Now he says factors uniquely. So let's talk about that. What does he mean by that? In other words, suppose that we also had that alpha was equal to, say, beta phi, where beta was some other map competing for the role of alpha bar. Then we can show that beta has to be equal to alpha bar. I do need to assume that beta is where going a mapping from G mod the kernel to H, all right? And phi is still the coset map. So what happens here? if you take beta, phi, and you give it to x, it's equal to alpha of x, right? By assumption. But what's this? Beta, what's a phi of x? What's phi of x? It's still kx, right? So beta of kx has to be equal to alpha of x, right? But that's equal to alpha bar of kx for all kx in the quotient. So therefore, beta is equal to alpha bar. And that's what he means by factors uniquely. This little argument I just gave you is not in the book, annoyingly. It's not that hard to show uniqueness, but that's what's meant by uniqueness. I mean, he has a calculation which he says uniqueness, but I know you guys, when you read that sentence in the book, it's not going to make sense to you. I hope when you look at what he just did, it makes sense to you. If we had another mapping, which also tried to play the role of this arrow in the map, it has to be alpha bar. That's the one and only map which does that. Well, guys, next time, I'll give you a couple of examples of the first isomorphism theorem. Then we'll be off to chapter 8. Exciting, right? Yeah, we'll come back to rings. What I'm doing is I'm just cleaning up. We're kind of going into survey mode next time. I will stop proving things. I'll just start stating things. And I'll try to we'll try to appreciate some of the deeper results in group theory, which are proved in chapter 8, which I will just state for you guys, and we'll try to kind of smell the roses.